let's go. We gotta get over there. Going over to Carl's for a nice video. Hey, what are you guys doing here? It's not supposed to be in my shop. You're supposed to meet me at Carl's. Come on now. I told Harold over at Amateur Redneck Workshop he was supposed to get a hold of the monkeys up in Canada, Pierre, Phil, and Robert. Oh man. Well, I know Randy Richard can't make it. He's snowed in. It's cold here in California for all you people. And, oh my God, I know Ray Cornelia, he's got his dick stuck in a vise. It's his new hobby. All right, well, come on, we're going over to Carl's. Come on, Howie.
Well, good morning, everybody. We're back in my shop, as Chuck has told you. And one of Chuck's subscribers dropped the monochromatic light off for us to display. The backstory is that he wanted to see how flat his Bridgeport mill would mill, and he thought he could check that with an optical flat and a monochromatic light. After experimenting just a little bit with it, we have found that even ground surfaces right off the surface grinder will not show the fringes that are characteristic of a flat checking an optical flat checking a flat surface. So I don't think he's going to be able to check a fly cut surface using this, but it provides us something to talk about a little bit. The purpose of an optical flat is to check flatness of a surface within millionths of an inch, down in the length of the wavelength of light. And what happens is that as light bounces around in there, it interferes with each other, and at some points it develops a bright spot, at other points it develops a dark spot, and that's what you see. And let me tell you, that's the limit of my knowledge. This is the very beginning of our experimentation with it, and we just wanted to show you this just for fun. We'll move on next to my big project. I showed you this in the last video. This is a regular Spindex that I converted by reversing the spindle in the casting so that the collet goes at this end rather than down here by the index wheel. And that's just a much better design, and I like this a lot. The function of this, one of the reasons for this was that it was a practice for what I'm going to show you next. So we'll move over here to the next piece. Okay, I took another Spindex and I converted it to a indexing head that is driven by a little stepper motor. The stepper motor's up here. It is driving the worm via a timing belt and little sprockets, and then you can barely see the worm, the little brass thing down inside there, the gear down in there. And it is connected to the spindle through the shaft collar. There's 3 screws, you can see them here, that are screwed through the shaft collar, past the spacer, and tapped into the gear. Later in some still photos, we'll show you a little bit more detail of how this was done. Right now, if you look at the dial indicator, I have the worm block is fixed. That's in the best position for this to drive. It turns out there are some cumulative errors, and I'm going to show you those by loosening the block. And if you'll watch the dial indicator, you'll see that there is a once per revolution error in the pinion. The worm, excuse me, I keep thinking gears. That's in the worm. The shaft that it's running on indicates that about 3 to 4 tenths run out. The total run out here is indicating at around 2.5 to 3, but we are on a lever arm, which is twice the actual run out at this point, and so I'm looking at maybe at this point maybe 1/1000. So that is a cumulative error between the run out of the shaft and the run out of the pitch circle of the worm to its bore. And there's nothing I can do about it. As it turns out, when this is clamped in a good position, what's actually happening is that the worm shaft is being bent just a little bit as it turns. If we watch this for a longer period of time, and we won't spend the whole revolution looking at this, we'll see that there is a once per rev error that is due to the worm gear itself. Now there's several sources of error on that, and the first being how close was it machined, and the second, how closely was I able to hold concentricity of the initial bore to the new bore. And I have a still photo that'll show you that. But right now the thing of interest is this is working. Turns out that I bought a 1/4 inch wide belt. It does not have enough torque to transmit the full torque of the motor. It should have been a 3/8 wide belt. That doesn't really matter. It has enough torque to do the job. And so we'll leave that. Looking over here at the controller, Chuck's going to move the focus just a little bit. This is a little interesting bit of electronics. Just basically putting pieces in a box and bolting them down and wiring them together. The controller itself that does the calculation of the indexing was from Stephen Ward in the UK. And we'll put up his website in the video later. So he provides a drawing for this, and I printed this out on photo paper, laminated it, machined the box, glued this on, put everything inside, and it runs. It runs in continuous mode, as you can see it running now. It does not work in stepping mode, in indexing mode. And the reason for that, it turns out, is that there's a limitation in the software on the way that it calculates the stepping for angles that are not even divisors of 360 degrees. And so I bought a Gecko drive, one of the best. I thought, oh, microstepping, 10 microsteps. Ooh, that's good. So I bought a 10 microstepping drive. Well, it turns out I can't use a 10 microstepping. I have to use, at the maximum, a 5 microstep. So I purchased another one. This one is capable of being set for full, half, 1/5, or 1/10 microstepping. And that will work. The controller that's in here now is going to be repurposed. I've decided that, boy, this indexer works. Yep. Okay, here we are boring the bearing block. The boring bar has an R8 taper. It's 1.5 inch diameter, solidly held in the spindle of the Bridgeport. Notice that it's not a boring head, it's a boring bar with a offset tool holder. And I built this for another project. I will show you more detail about this when I actually show you the project that it was built for. There are no calibrations on the bar. Not shown in this photo is the dial indicator that's used to check how far the bar is offset. The worm bearing block needs to be adjustable to set the gear mesh, and it should be able to be moved to clear the worm from engagement with the gear so that the spindle of the Spindex can be rotated by hand if necessary. A radial slot was drilled out and then milled to size on the rotary table. The body of the Spindex was cast with bore vertical so that the base flange has draft angle in 2 directions. So I milled the edge of the Spindex block parallel to the spindle, and you can see the spindle sitting on V-blocks. And you can also see the indicator where we checked the parallelism of the spindle to the mill table. We got it within around 5/10, and we decided that was good enough. This picture shows boring the worm gear out from 5/16 stock bore to 45 millimeter. We'll see in the next photo that there's not a lot of stock left, and that meant that it was a difficult job to clamp. You can see the clamps just barely holding on the rim of the gear. I don't think I got this perfectly concentric, but I don't know any other way that I could have done it. So that was the, as I said, the best that I could do. So in the next photo, we'll take a look at what it looks like when it's finished. The next operation on the worm gear was to mill the cast surface underneath the rim flat to seat up against a spacer ring that I had to make. And this gives you kind of a visual impression of just how little of the gear was left. There's absolutely nothing remaining to secure the gear to the spindle of the Spindex. and that was done by screws into the gear from the shaft collar. A little hard to see. If you look carefully, you may be able to see three little drilled and tapped holes in the rim of the gear. The Cincinnati mill uses a slightly different set of collets. These are made by Superflex. They're also known as monoset collets because Cincinnati used them for their monoset grinder. They were available from 3/16 to 1 inch. I go from 3/8 to inch. This is a Morse Taper 3 adapter, and this is the small collet set adapter. It's got a regular nut, and these are the collets. They start at 1/8 and they go up to 1/2 inch. So I have a full set of collets for this. This particular mill, let me set these collets away for just a little bit. This particular mill was designed as a die and mold making machine, and let's see. We're going to stop right here. I'm going to have Chuck move the camera so you can see what I want to demonstrate just a little bit better. We're going to put the camera over on this side. I talked earlier about this mill and the fact that in the position where the camera is now, which is to the right of the spindle casting, there was a great big three-dimensional hydraulic tracer head. And what you would do is out here to the right, you would put the template and set the machine running, and it would carve out the interior of the mold. Well, but in addition to this, the Cincinnati mill, called the Contour Master, has the ability to tilt the head. Now watch what happens. If you look right here at the tip of the end mill, the cutting point stays, the center of the mill stays in exactly the same location. That is, the center of rotation, the center of nodding of the head is right there at the end of the end mill. And so you can, with the head at 90 degrees to the table, you can carve out the interior of the mold, and then you can go 5 degrees, and without changing the inside dimension, you can cut the draft angle on the wall of the mold. So that's what this particular mill was designed for, and the reason for its very, very strange ram and head assembly. All right, we're going to go down to the left end of the table, and I want to show you just a little bit about the lubrication system, and then following that, we will show you some more details in the stills that I have. Just a quick look at the lubrication system. There were 13 ports in the original configuration, and I left it like that. I just made no changes in the layout of the system inside the machine itself. The original, this set of 9 was originally right inside here, inside the saddle. These 4 were way up inside the interior of the knee. That was one of the most difficult disassembly projects I've ever undertaken, and I can't imagine what it must have been to assemble that inside there. Chuck and I looked at here's the pump that supplied these 4 ports, and we looked inside there. There's 3 or 4 fittings and the pump body itself. We have no idea how that was put in place. It's possible that we can see a slight shadow that may have been somewhat pre-assembled and fit in somehow, but we don't know what it is. So here are the metering units. There's 4 here, and of course the various fittings. The pump now, excuse me, let me go back. There's another pump up here that fed only these 9 in the saddle, so the 2 systems were originally separate. I tied them together via this jumper with a single larger pump, and so far so good. I've had a few minor leaks. There's a little bit of seepage here and there. I may have to live with that. I'm slowly finding leaks and tightening down nuts. I did have 1 leak in the push to connect fitting. So that project is done. The paint job is done. And okay, we'll pause for just a second and I'll show you one more detail on the mill. Oh, before I do that, as long as we're down here on the floor, cutting these tubing the cutting, all the original copper tubes were cut down inside some casting someplace. And the ideal tools for that turned out to be one of the Harbor Freight air-powered saws with a 32 tooth blade, and I held the copper tubing in the other hand with the line pliers, and I just kind of went like this and just went, and it just chopped them right off. A little tiny bit of deburring. The cut was pretty smooth, and so far I've had no real problems with the 12 of the push to connects. I had to replace one, but that may have been because I didn't have the nylon tubing inserted fully. Hard to say. I just changed the coupling while I was working up inside there. Okay, one more thing on the mill, and then I'll show you something really different. This machine was completely worn out when I bought it. Maybe I shouldn't have bought it, but hey, it worked pretty good for me for some years. Eventually I scraped the money together, and I had the table surfaces and the saddle and the top of the knee reground and turkited. And of course the recommendation is when you turkite is that you install wipers, which it took me a while to get around to. But I finally figured out there's a 1/8 inch of felt and a couple of pieces of aluminum to compress it and hold it in place. This little box here is to go around the gib and gib screw, which stick out about 1/2 inch. And so I just made a little box and a top, and there's some felt in there so that all the surfaces are kept clean, and eventually as these soak up oil, they'll distribute oil very nicely across the surface. So that's a nice addition, something I've been wanting to do for a long time. Chuck said he wanted to do a panoramic view of the mill just to give you an idea of what it all looks like. And so while he's doing that, I'll make one comment. Clearly the mill had been painted 3 or 4 different times, and it had worn differently, and it was kind of a hodgepodge. And so I decided, well, while it's apart, it gets a paint job. This is not a concourse job. I did a little bit of glazing putty on it here and there. But I didn't sand it out perfectly, and this, that, and everything else. It just is a decent paint job, and that's all it needs. Going up here, Chuck's about to show you the DRO. Sargon, sold by Enco years ago. Unfortunately, during the work on the mill, the table spar got damaged. I pulled the reader out, and it's going to LA this week for $150 plus shipping repair. But you know, those things happen. We'll go around here just a little bit more to the right, and I can show you this very, very early model Fincor VFD. I like this thing. You know, I could buy a Teco for a couple $100, maybe even less. It's only 1 horsepower. That is not much bigger than the 4-square box here. And look at all this stuff inside there. And I just say, you know, this thing works. It develops plenty of torque. I've already built all the wiring for it and everything. And so it's just simply staying there until something happens to it. Just a couple minutes for the Chuck subscriber who has the same mill. The problem is that you can take a Bridgeport apart with not much more than a set of wrenches and a socket set. This mill requires some special tooling. There are some pin spanners. There's 4 pin spanners. Turns out this one's identical to this, and I don't know whether I didn't know that or if there's a reason for different shaft size. I think I just made a mistake and made another one. These two are, I think, used in assembly of the head. I think this one's also assembly for the head. This is for a nut on the top of the spindle on the bearing nut. And this plate is for the side plate on the knee, and you have to get that plate off in order to extract the knee elevating screw, and you have to have the screw out in order to get your hand in far enough to work on the lubrication system. So you need at minimum to be able to make this, these two, and this in order to disassemble your Cincinnati mill. The saddle you can turn upside down with just two different hoists. The knee, again, you need two hoists, but there's nothing to grab a hold of. I'm not sure how they did it in the factory. They had to have had some kind of fixturing. I wound up drilling and tapping holes in the knee, and I attached these hoist rings, and so then I could pick it up on one end, and then drop it, set it on a surface, and tip it over just slightly, and turn it over. So you'll need, I think you can do it with one. I did it sometimes with two, but as I said, if you're planning to use an engine hoist, you're going to need some ingenuity in order to be able to work on this thing. And you definitely will need access to another milling machine in order to make some of these parts.